Did you know that light races across the universe at nearly 300,000 kilometers per second? Yet it's bound by a cosmic speed limit no one can break. Feel that gentle hum under your feet. Just the starship's engines, a soft vibration through the deck plating as we drift deeper into the velvet void. Your console glows faintly, casting warm patterns across the cabin, mirroring distant stars dancing on the viewport. The air smells crisp, cool, and calm, a quiet contrast to the infinite silence pressing in from beyond the glass. You might notice a tiny, almost imperceptible shift as the ship nudges its course, keeping us perfectly aligned for this slow, cosmic journey. Here we are, just you and I, floating between the stars, ready to explore one of the universe's quietest mysteries: why light moves the way it does. Whether you're curled in a cozy corner with a warm mug beside you, or simply letting your mind drift, there's no rush here. We're gliding gently, letting the ship guide our curiosity. Why does light race so fast, yet obey invisible cosmic rules? It's the kind of question that invites a quiet wonder, don't you think? Every time you flip on a lamp, shadows vanish and the world brightens in an instant. Light lets you see far-off nebulae shimmer outside, or even just the reflection of your own face on the glass. But what is it, really, this thing that paints the universe and illuminates our world? Is it a restless messenger, a ripple, or a tiny bullet streaking across the void? The answer, as always with the cosmos, is beautifully strange, a bit of everything, and yet uniquely itself. Let's meet the stars, tireless couriers, photons. These are the packets of energy that make all light possible, darting endlessly through the stillness of space at the fastest speed the universe allows. But they aren't little specks or marbles. They have no mass, no need for rest, and they follow rules entirely their own. Maybe they're more like fleeting thoughts made real, eternal travelers moving through the quiet cosmic night. And just when you think you have a handle on them, photons reveal another facet of their captivating nature. For while they behave as these discrete packets of energy, they are simultaneously waves, not like the gentle undulations of water against our hull or the familiar way a ripple spreads. These are electromagnetic waves, an exquisite choreography of unseen electric and magnetic fields. Imagine two invisible forces, perpetually intertwined, vibrating in perfect harmony, always at right angles to each other, and always propelling forward. It's a silent, cosmic ballet, a synchronized dance of energy unfolding across the vastness, isn't it? An elegant, invisible rhythm pulsating through the universe. Now, this particular aspect is crucial, a key difference that allows us to witness the universe in all its glory. Unlike the faint hum of our ship's engines that needs the hull to transmit its vibration, or the ripples a dropped tool would make if we were on a liquid planet, light doesn't require a physical medium to carry it. Sound needs air, water waves need, well, water, but light just is asterisk. It cuts straight through the profound emptiness of the void, unimpeded. That's precisely why, from our vantage point, you can gaze upon the fiery heart of a distant sun. Its light having traversed countless parsecs of absolute vacuum, reaching us without ever needing a cosmic pit stop. Quite remarkable, isn't it? And this light, this singular phenomenon, isn't limited to the shimmering blues and oranges you see out the viewport. Visible light, the familiar hues that paint our perceptions, is merely a sliver, a fleeting melody within the grand symphony of the electromagnetic spectrum. Imagine a cosmic piano, its keys stretching into infinity, far beyond the reach of human hands. Our visible light is but a few notes clustered in the middle, a small, bright octave. At one extreme, you have the languid, sprawling radio waves, undulations so vast they could gently embrace entire star systems. On the other, the fierce, piercing gamma rays, energetic bursts born from the heart of collapsing stars or turbulent nebulae, capable of slicing through almost anything. A bit intense, those ones. Between these cosmic extremes lie an astonishing array of other light forms, each with its own rhythm and purpose. There are the microwaves, quietly warming your rehydrated meal packs. Infrared, the warmth you feel radiating from the distant celestial bodies, or what guides your ship's thermal sensors. Then ultraviolet, an invisible reminder of solar flares, ready to leave its mark if you forget your space sunscreen. And X-rays, which allow us to peer into the inner workings of mechanics or even your own skeletal frame, yet still prove utterly useless when you're searching for that rogue glove. Why does the universe always do this to you? Such a mystery. Yet, for all their varied forms and functions, from the longest radio wave to the sharpest gamma ray, every single one of these electromagnetic wonders shares a profound constant in the absolute vacuum of space. They all travel at precisely the same dizzying speed. We speak of it as approximately 299,792,458 meters per second, a number so vast, so unfathomably quick, it almost loses its meaning. It's like asking the cosmos, how fast, and receiving the simple, yet profound answer, yes, absolutely. Imagine, if you will, a nimble courier of light, circling our home planet more than 7 times in the mere blink of an eye. Not bad for something with no obvious means of propulsion, is it? However, this phenomenal cosmic speed limit isn't a universal constant in all asterisk environments. Out here, in the pristine vacuum, light has a wide open highway, but introduce it to a denser medium, perhaps a nebulous cloud of gas, a pane of transparent alien crystal, or a swirling eddy of interstellar dust, and our swift travelers encounter resistance. It's not that the photons get weary, no. Rather, they engage in tiny, fleeting interactions with the atoms of the material, a brief dance of absorption and re-emission. Think of it like trying to glide effortlessly through a crowded marketplace. You're still moving forward, but there are countless gentle nudges and detours, slowing your overall progress. This delicate interplay, this momentary slowing and redirecting, is precisely what gives rise to the enchanting phenomenon we call refraction. It's the subtle bending of light as it transitions from one substance into another. That's why a distant nebula might appear distorted through a particularly thick patch of cosmic gas, or why a beam from our ship's spotlight seems to bend and shimmer as it passes through a planet's hazy atmosphere. Each of those breathtaking refractions, each sparkle from an icy comet, is a silent testament to light's journey being momentarily delayed, subtly rerouted, and scattered with gentle grace. A truly beautiful complication, don't you agree? And here lies the most intriguing nuance, a little secret of the universe. Even when light appears to be slowing down within these materials, the individual photons themselves are still zipping along at their maximum vacuum speed between those atomic encounters. They don't actually lose personal velocity. Instead, their path becomes a complex, stop-and-go itinerary. Imagine trying to speedwalk across a vast alien ballroom filled with enthusiastic, swaying beings. You're still moving fast in your individual strides, but the constant weaving and pausing to navigate the crowd drastically reduces your overall speed from one end of the room to the other. It's a clever cosmic trick, isn't it? Speaking of those beautiful complications, let's turn our gaze to the vibrant spectrum of color itself. When you observe the shimmering aurora borealis dancing across an ice giant, or the iridescent sheen on a patch of interstellar gas, what you're witnessing is light being gently coaxed apart, revealing its constituent wavelengths. Each distinct shade within our visible spectrum corresponds to a different length of that electromagnetic wave. The deep, warm reds are like long, slow breaths, expansive and unhurried. The sharp, vibrant violets, in contrast, are quick, energetic pulses, almost twitchy in their eager frequency. But remember, whether a languid crimson or a vibrant indigo, each is fundamentally still a photon, a tiny messenger of energy. Still, you perceive them as vibrant hues, don't you? It's simply the dance of electromagnetic waves, each one a unique vibration, a frequency whispering its presence to the universe. Your own eyes, those remarkable instruments, possess special cells, the cones exquisitely tuned to capture these subtle variations. That's the secret to how you witness color. An apple isn't inherently red, you see. It's merely reflecting the specific wavelengths our brains interpret as that rosy shade, while quietly absorbing all the others. In essence, every color you've ever seen is your mind's most elegant interpretation, a beautiful best guess based on which tiny vibrations have gently brushed against your retinas. A truly marvelous illusion, isn't it? And if this isn't already wonderfully strange enough to ponder as you drift here, consider this. Light itself carries no rest mass. That means, unlike you, or me, or even the slightly stern-looking maintenance bot down the corridor, light doesn't require energy just to be in motion. It always moves. There is no alternative for it, no quiet repose. Should a single photon ever truly stop, it wouldn't be pausing for a moment's breath. It would simply cease to exist. Motion or nothingness, all or gone. That's not merely poetic, my friend. It's fundamental physics. It reminds you of the deep void outside, always in motion, even in its apparent stillness. You might feel a soft vibration humming through the ship's hull, a gentle reminder that even we are forever in motion, chasing the light. So, here we are, navigating through the cosmos with these incredible, massless packets of pure energy. They behave like both waves and particles, traveling at a universal, unwavering speed, capable of interacting with atoms, bending around distant celestial curves, and bouncing off the polished surfaces of your ship, all while delivering the very experience of sight and color directly to conscious minds like yours. And frankly, that barely scratches the surface of its mystery. But for now, as the gentle hum of the life support system fills the quiet cabin, let's simply hold on to this image, light as a tireless, restless traveler, woven from no substance but pure, unfathomable energy, never pausing, never truly sleeping, always tracing the delicate outlines of everything we comprehend. It's light that unveils the countless stars stretching beyond our viewport, reflects in the console lights that cast a soft glow across your face, illuminates the faces we hold dear, and reveals the treasured pages of your favorite data slate reads. And it accomplishes all this while obediently adhering to one of the most curious regulations in the entire universe, a speed it will never ever exceed nor ever fall beneath. Light isn't just what permits us to see. It's the very voice of the universe, whispering its ancient stories directly into our eyes. Isn't that just like space, always holding the grandest secrets in plain sight? Now, let's take a wonderfully gentle step back in time, shall we? Far, far back, long before our intricate satellites dotted the inky canvas, before the precise beams of our lasers cut through the void, and long before physicists possessed their high-tech instruments to decipher the universe's most guarded secrets. Picture a world illuminated only by the flicker of earthly fires and the distant silver gleam of stars. In such a time, truly grasping something as elusive as the speed of light wasn't just difficult, it must have seemed utterly absurd. The recycled air feels cool on your skin, but the warmth of historical wonder begins to stir within you. For the vast majority of human history, people simply believed light moved instantaneously. It just was asterisk. You ignited a candle, and the room was immediately bathed in its soft glow. The distant sun broke the horizon, and the world instantly transformed into a canvas of golden hues. No waiting, no perceptible delay. It seemed entirely obvious, didn't it? Why would anyone ever conceive of it otherwise? Even the ancient Greek philosopher Empedocles, one of the rare few who dared to suggest that light might possess a finite speed, wasn't taken seriously at all. Aristotle, whose pronouncements had an unfortunate habit of cementing themselves as undeniable truth for centuries, deemed light instantaneous, and that, everyone thought, was that. Case closed, curiosity neatly shelved, a familiar pattern, perhaps. But then, as so often happens, a singular mind dared to question. Enter Galileo. Now, Galileo was certainly not one to simply accept things because an influential voice had declared them so. He delighted in prodding at things, dropping them from lofty heights, and, famously, turning his primitive telescopes towards celestial bodies like the moons of Jupiter, which you can see in miniature on your navigational display. Around the year 1638, he embarked on an attempt to measure the speed of light in what truly might be the most adorably optimistic experiment ever conceived. It was a charmingly hopeful idea, wasn't it? The concept was disarmingly simple. Galileo and his assistant each carried a lantern, which they kept covered, and then positioned themselves on hilltops, roughly a mile apart. Galileo would uncover his lantern first, and the moment his assistant perceived that distant flash, he was to uncover his own in response. Galileo would then attempt to measure the fleeting interval between sending his signal and seeing the return flash. Even under the most optimal conditions, this experiment was spectacularly ambitious. The mere human reaction time, you see, clocks in at about a quarter of a second. Light, conversely, requires less than a 10,000th of a second to traverse a single mile. It's akin to trying to gauge the speed of a high-velocity projectile using nothing but a sundial. Still, one cannot help but admire the sheer effort. Unsurprisingly, Galileo concluded that if light indeed possessed a finite speed, it was simply far, far too rapid for his earthly methods to detect, which was absolutely true. Yet, the critical question had at least been posed. The gentle hum of the ship reminds you of how far we've come. Fast forward just a few decades to the year 1676, and introduce a Danish astronomer named Ole Rachmer. He would, quite by accident, stumble upon the answer by intently observing something incredibly distant: the graceful dance of Jupiter's moons. You can just make out the gas giant through the forward viewports, a swirling marble of silent majesty. Rachmer meticulously tracked the orbit of Io, one of Jupiter's many loyal companions, which zips around the colossal gas giant with the regularity of a cosmic clockwork. By carefully noting precisely when Io vanished behind Jupiter and when it reappeared, he began to notice something decidedly peculiar. The timings, you see, were not consistently identical. Sometimes Io would reappear a little later than expected. Other times, it would emerge a touch early. At first glance, this might suggest an issue with Rivmer's own measurements, but he had a truly brilliant, almost defiant thought. What if the inconsistency wasn't with Io at all, but with us? What if the subtle delay he observed was simply due to the fact that Earth was sometimes farther away from Jupiter, meaning the light from Io had a greater distance to travel? And just like that, with a single, profound flash of insight born from simple observation, the revolutionary idea of light, possessing a measurable, finite speed, began to coalesce into real, scientific understanding. From these subtle timing discrepancies, Rachmer made a truly astonishing estimate. He calculated that it took light approximately 22 minutes to traverse the entire diameter of Earth's orbited distance. We now understand to be roughly 186 million miles. Not bad for a few centuries ago. His estimate wasn't absolutely perfect, of course, given he lacked accurate distance measurements and our precise modern clocks, but it was nothing short of revolutionary. It quietly, yet firmly, declared to the world that light takes time to travel. Not a lot of time, perhaps, but enough to genuinely matter. The shifting gravity in your cabin gives you a gentle push, a subtle reminder of the profound distances we are discussing. Later, in the early 1800s, a determined physicist named Hippolyte Fizeau decided to try something a little more grounded, more earthbound. His ingenious method involved a focused beam of light, a precisely rotating toothed wheel, and a mirror positioned several miles away. Here's how it ingeniously operated. The beam of light was first directed through a narrow gap between the teeth of the spinning wheel. It then embarked on its journey to the distant mirror, where it gracefully bounced back. If the wheel was rotating slowly enough, the returning light would find its way back through the very same gap it had initially departed from, remaining visible. But if Fizeau increased the wheel's speed, the returning light would instead strike a solid tooth, rather than a gap, and thus be completely blocked from view. Quite clever, really, for the time. By meticulously adjusting the wheel's rotational speed, Fizeau could pinpoint the exact moment when the light beam was fully extinguished. This critical point indicated that the light had precisely enough time to travel to the mirror and return, while the wheel had rotated by exactly half a tooth's width. Using the known distance between the wheel and the mirror, and the wheel's precisely measured rotational speed, he then calculated the speed of Anso. As we gently drift through this cosmic sea, perhaps you notice the way the distant starlight plays across the polished surfaces of the console, a silent, flickering dance. It reminds us of how, centuries ago, brilliant minds on a small blue planet first began to truly chase these ethereal light beams. One ingenious soul, imagining a grand gear and mirror setup, calculated light's pace at roughly 193,000 meters per second. Not bad for an old clockwork trick, wouldn't you say? Later, another refined the pursuit with gracefully spinning mirrors, not only sharpening the measurement, but also revealing a subtle truth. Light, this most nimble traveler, actually slows down ever so slightly when it dips into water, compared to the open air. A hint, a quiet whisper, that the universe interacts with its own fastest messenger in curious ways. This quest for precision drew in many, but perhaps none more famously than Albert Michelson. Imagine him, in the late 1800s, dedicating himself to this very question, meticulously aligning mirrors in long, enclosed tunnels, timing every reflection with breathtaking accuracy. His dedication earned him a pinnacle of human recognition, the Nobel Prize, a truly remarkable reward for essentially playing a cosmic game of tag with light, using nothing but mirrors and sheer cleverness. Today, our tools are, naturally, a little more advanced. Lasers, atomic clocks, the very satellites that guide our journey. We've even inverted the equation, defining the meter itself by light's unchanging speed. Since 1983, a single meter isn't just a measure of length. It's precisely the distance light travels in a tiny fraction of a second. Isn't that just like space, turning everything on its head? We don't chase light speed anymore. Its speed now defines our world, a fundamental constant. Yet, it all began with simple observations, spinning wheels, and the quiet wonder of whether the universe might hold secrets, moving faster or slower than we perceived. And perhaps that's where the real beauty lies. The speed of light isn't merely a number. It's a profound narrative woven through time, a testament to curious minds and their elegant, persistent pursuit of understanding. It proves that even the universe's swiftest phenomenon couldn't outrun human curiosity. So, now that we've followed our speedy photon friend and the long, fascinating journey to measure its incredible pace, we arrive at a question that often makes physicists, and perhaps even our ship's navigation computer, ponder late into the night. Why doesn't light simply go faster? It does seem like a rather specific number, doesn't it? Why exactly 299,792,458 meters per second? Why not a nice, rounder number, or better yet, infinite? Why must light, this ethereal, massless bundle of energy, comply with such a strict, universal speed limit? To truly grasp this, we'll need to take a calming stroll into one of the most elegant and, frankly, mind-bending corners of physics, the realm of electromagnetism. More specifically, let's conjure up the memory of a brilliant mind named James Clerk Maxwell. Back in the 1860s, Maxwell took all the scattered knowledge about electricity and magnetism, think Benjamin Franklin's daring kite experiments, or Michael Faraday's ingenious coils, and distilled it into 4 stunning mathematical equations. They sound a bit plain, known simply as Maxwell's equations, but they describe how electric and magnetic fields playfully interact, shift, and flow. You don't need to worry about the equations themselves. No one's going to quiz you on them as we glide through the void. But here's the truly dreamy part, a moment that must have sent shivers down Maxwell's spine. When he combined these elegant equations, he unearthed something utterly extraordinary. They precisely predicted a particular kind of ripple, an electromagnetic wave that would spontaneously emerge whenever electric and magnetic fields wiggled in just the right cosmic rhythm. And this wave, this predictable ripple, would always travel at one specific speed. When Maxwell meticulously performed the calculations, plugging in the known values for electric and magnetic constants, he arrived at a number. That number, you've guessed it, was precisely 299,792,458 meters per second. Maxwell was stunned. He'd found a fundamental speed, a cosmic constant, embedded deep within the very laws governing electricity and magnetism. And the kicker, that exact number perfectly matched the best available measurements for the speed of light. This wasn't merely a coincidence, it was a profound revelation. Light, Maxwell realized, was nothing less than an electromagnetic wave itself, a self-sustaining ripple of electric and magnetic energy zipping through the vast emptiness of space at a pace dictated not by chance, but by the very architecture of the universe. Let that quiet thought settle over you. Light speed isn't a mere happenstance. It's inherently woven into the equations that govern the fabric of reality. It's not as if the universe just randomly spun a dial and landed on that number. No, it's more like the universe must operate this way. If electric and magnetic fields exist, and we certainly feel their subtle influence even now, maintaining our ship's systems, then light must travel at this specific speed. So, that's a significant part of the answer. Light moves at the speed it does because that's the only speed electromagnetic waves can achieve in the vacuum of space. Anything faster or slower would simply shatter the fundamental laws as we currently understand them. But now, as we continue our gentle journey, let's venture one layer deeper. Why can't anything go faster than that? In our everyday lives, speed often feels optional, doesn't it? If your ground vehicle can go 100 kilometers an hour, it can probably push to 110 if you're feeling a bit daring. But with light, there's no upgrade, no extra push, no speeding ticket, just a hard, unyielding stop to uncover the reason behind this ultimate cosmic speed limit. We need to bring in someone whose name you've almost certainly encountered, a quiet revolutionary named Albert Einstein. In 1905, Einstein unveiled his special theory of relativity, and with it, he fundamentally reshaped our understanding of existence itself. One of the cornerstone ideas of special relativity is this: the speed of light in a vacuum is absolutely the same for all observers, irrespective of how fast they themselves might be moving. Now, that might sound rather straightforward, perhaps even a bit tame, but it's actually utterly mind-bending. Imagine for a moment that you're aboard a train hurtling through space at, say, 90% the speed of light. Impractical for a comfortable nap, perhaps, but excellent for a thought experiment. You click on a small flashlight. You might intuitively expect that the light beam emerging from your flashlight would appear to a stationary observer on a distant platform to be moving even faster, as if your train's speed was added to the light's speed. But no, both you inside the ship and the observer on the distant platform would measure the speed of that very light beam as exactly the same. Not a whisper more, not a flicker less. To make such a peculiar truth possible, reality itself has to cleverly twist and bend around this unwavering rule, ensuring that no one, no matter how swiftly they travel, can ever perceive light breaking its own inherent pace. Time stretches, distances contract, mass increases, the very universe subtly adjusts its rhythm. You might notice a subtle resistance, a quiet, almost imperceptible pushback as you ponder the idea of truly picking up speed. If you, our intrepid voyager, were to ignite every booster, every theoretical engine, and try to accelerate towards the dazzling brilliance of light's ultimate pace, you'd encounter a peculiar, fundamental hurdle. As your vessel gathers momentum, gaining more and more velocity, an odd thing happens. Your mass begins to swell. Not like you've indulged in too many stardust cookies, no, but in a deeper, more profound way. It demands progressively greater amounts of energy, to nudge you just a fraction faster. Imagine the gentle hum of your ship's engines working harder, the soft vibration through the hull intensifying as you near the speed of light, where your theoretical mass would spiral towards infinity. And to reach that unreachable goal, you would, in turn, require an infinite wellspring of energy. A rather tall order, wouldn't you agree? Even for the most ambitious journey across the void. So, no matter how much you yearn to chase those distant stellar glows, how relentlessly you pursue the horizon of ultimate speed, you can only ever get incredibly, astonishingly close. You can embrace the light, ride its very edge, but you can never quite touch it, never fully catch up. This, you see, is why the speed of light isn't merely the speed of photons. It is, quite beautifully, the universe's ultimate speed limit. It's the invisible, elegant upper boundary on how swiftly information, energy, or indeed anything with a measurable mass can traverse the cosmic tapestry. A serene barrier, a profound boundary, etched into the very fabric of space-time itself. Nothing to worry about, just a quiet, unwavering truth. And here's an even more peaceful thought to settle into. If this magnificent cosmic speed limit didn't exist, if light could just zip off into infinity, everything as we know it would gently unravel. Causality, that fundamental concept where causes unfailingly precede their effects, would simply fall apart. You could, theoretically, witness an effect before its cause, or even somehow send signals backward through the flow of time. Can you imagine the chaos? A bewildering dance of time travel, mind-bending paradoxes, a serious cosmic headache for logic itself. Instead, the universe, in its quiet wisdom, protects us from such delightful nonsense with this exquisite little speed cap. It keeps everything ordered, wonderfully predictable, and utterly calm. No matter how much the cosmos stretches or swirls around us, the speed of light remains constant. So, the next time you find yourself gazing at the delicate dance of starlight reflecting on your console, or perhaps the subtle, distant shimmer of a nascent nebula, remember, those ancient beams of light didn't just happen to arrive. They followed a sacred, unbreakable rule, one written into the very bones of physics, a silent decree that states, this far and no farther. It's a limit, yes, but a limit that bestows upon the universe its magnificent structure, its unwavering stability, and its breathtaking beauty. Light doesn't travel faster, not because it's weak or dilatory, but because it is perfect exactly as it is, gracefully bound to a speed that ensures time flows ever forward, keeps causality beautifully intact, and allows us to comprehend the world in a way that would otherwise be utterly impossible. And honestly, for something that effortlessly spans the vastness of space at nearly 300,000 kilometers per second, that strikes me as a rather elegant and dignified pace. Albert Einstein, now there was a mind. He possessed a rare gift for gently turning reality on its head, only to make it all seem perfectly obvious in hindsight, almost as if the universe had been softly whispering its secrets all along, and he was simply the first to truly listen. When he unveiled his theory of special relativity in the year 1905, he didn't merely tweak the existing rules of physics, he rewrote them entirely. At the serene heart of his groundbreaking theory lay a wonderfully bold declaration. The speed of light in the profound vacuum of space is absolutely constant, not just generally consistent, not simply almost steady if you're not moving too briskly, but an utterly, unequivocally constant number for every single observer, everywhere, always. It's a rather tranquil thought, isn't it, as you drift deeper into the quiet hum of the ship? Yet, It subtly redefines everything you might think you know about motion and the gentle passage of time. Imagine, if you will, that you're suspended in your ship, peacefully gliding through the endless void, cradling a simple flashlight. You activate it. A pure beam of light effortlessly shoots out ahead of you at, let's murmur it together, precisely 299,792,458 meters per second. Now, picture someone else, perhaps your seasoned co-pilot, gracefully flying past you in their own vessel, moving at half the speed of light. From their perspective, you and your ship are zipping by like a beautiful, fleeting blur against the distant stars. Yet, when they meticulously measure the speed of that very same beam of light emanating from your ship, they don't perceive it as moving any faster or slower. They too measure it at precisely 299,792,458 meters per second. Isn't that just deeply, profoundly weird? Why does the universe always do this to you? In our everyday world, on our familiar planets, speeds intuitively combine. If you were strolling along a moving walkway at a bustling spaceport, your pace would simply add to the speed of the moving belt. But with light, it's entirely different. The walkway could be hurtling through space. You could be effortlessly floating. The flashlight could be spinning. And yet the light speed remains precisely the same for all of them. So, what gives? Einstein's solution, truly, was beautifully unsettling in its simplicity. It's not the speed of light that ever changes. Oh no, it's everything else. The very flow of time, the expansive dimensions of space, the subtle passage of moments, the perceived size of objects. All of it gently bends and stretches, subtly shifting to preserve that one sacred, unchanging number. Let's gently explore these captivating consequences. First, we encounter a phenomenon known as time dilation. This concept is a firm favorite among aspiring astrophysicists and visionary science fiction authors alike, a truly mesmerizing idea. The faster you journey through the vastness, the more leisurely time itself appears to flow for you when compared to an observer who remains relatively at rest. This isn't merely a subjective sensation. It's a very real, precisely measurable effect. For instance, imagine your ship accelerating to, say, 90% the speed of light. To you, inside the serene confines of your vessel, everything feels perfectly, utterly normal. You might quietly sip a drink, perhaps lose yourself in a book, or mildly wonder why you packed so few socks for such an epic voyage. But upon your return to our familiar blue marble Earth, you might just find that significantly more time has elapsed for everyone else than for you. Years, perhaps even decades, could have gracefully drifted by. While your own journey felt quite short, Earth itself continued its steady march through the cosmos, aging without you. This isn't just a captivating theory confined to dusty old journals. It's a concept we've meticulously tested and confirmed. Tiny particles called muons, which are created high in Earth's protective atmosphere by cosmic rays, typically decay in mere microseconds. Yet, when these particles are hurtling along near the speed of light, their internal clocks subtly slow down, allowing them to persist longer, long enough, in fact, to reach the ground and be dutifully detected. Time, you see, actually stretches for them as they move, a silent testament to the universe's pliable nature. Next, we encounter length contraction, the peculiar, intriguing twin of time dilation. When you journey at these incredibly high velocities, objects that lie in the direction of your motion appear to become shorter. Not merely an optical illusion, mind you, but a true physical reality. Your magnificent spaceship would literally measure as being shorter along its path of travel, almost as if the universe is giving it a gentle, imperceptible squeeze. Now, before you start envisioning yourself and your cozy cabin folding into an uncomfortably compressed cube, understand that this effect only becomes truly noticeable at speeds remarkably close to the ultimate cosmic limit of light. For our everyday travels, your standard lander, a sleek orbital shuttle, or even a very enthusiastic asteroid jogger, the effect is so infinitesimally small it might as well not even exist. But near light speed, the universe gets wonderfully squishy. Then there's the relativity of simultaneity, which, while sounding like a delightful tongue twister, is actually a rather lovely bit of mental yoga for your mind to drift through. It means that events which appear to happen at exactly the same moment for one observer might not, in fact, be simultaneous at all for another observer who is in relative motion. A subtle dance of perspective, a quiet reminder that even time's progression can shift depending on your gentle journey through the void. You drift gently, tethered by invisible currents within the quiet hum of your ship, starlight painting fleeting reflections across the polished console before you. It's a curious thought, isn't it, that two moments, perfectly synchronized for you, might ripple into an entirely different sequence for another soul, simply because they are moving differently through this vast, still expanse. Imagine, if you will, observing a fleeting flash of light from a vessel speeding past us, its internal cabin brightly illuminated for an instant from the perspective of someone comfortably seated inside. That delicate burst of photons reaches both ends of their compartment simultaneously, a perfectly unified event. But to your watchful eyes, here in the serene stillness of the void, you'd perceive the light striking the rear of their cabin first, just a hair's breadth before it touches the front, as the forward section subtly pulls away from the flash. Both observations, both truths, are entirely valid. Time and space, you see, are not the rigid, universal constructs we once imagined. They are pliable, deeply personal, forever relative. All of this profound strangeness, time's peculiar stretch, distances subtly shrinking, the very notion of now fracturing into countless local moments, it all unfolds to safeguard one singular, unwavering constant: the speed of light. It's almost as if the universe itself, in its infinite wisdom, gazed upon this one intrinsic value and declared, everything else may yield, but this must stand unbroken. Think of it as a whispered cosmic covenant. In silent agreement to uphold the light's unyielding pace, the universe gracefully consents to warp and weave everything around it. It's a breathtakingly intricate ballet, a delicate balancing act designed to keep our sense of cause and effect, of before and after, perfectly intact. And speaking of causality, isn't it a soothing thought that this cosmic speed limit, this ultimate velocity, is precisely what safeguards the very fabric of our understanding? Because light can only traverse space so swiftly, information itself is bound by the same graceful tether. This means you can never, ever glimpse an event before it has truly unfolded, nor can you dispatch a message backward into the past. The light-speed boundary keeps our universe elegantly logical, reassuringly predictable, wonderfully tidy. Without it, things would unravel into beautiful, terrifying chaos. You could, perhaps, witness effects before their causes, or receive a communication before it was even conceived. Paradoxes would accumulate around us like cosmic dust motes on a long journey. Instead, the universe, with a gentle, firm voice, seems to murmur, "No, let's not wander down that path. Let's embrace order. Let's enshrine a maximum speed and hold it sacred. And it is here, in this profound decree, that the brilliance of Einstein truly illuminates the cosmos. He didn't merely describe the speed of light as a boundary. He unveiled it as a foundational pillar of reality itself, the very scaffolding upon which time and space are meticulously constructed. Even now, far from the subtle shimmer of distant galaxies, your personal navigation devices rely on his equations to pinpoint your location, preventing them from imagining you're adrift in an endless ocean. Particle accelerators hum with his insights, guiding their minuscule charges at astonishing velocities. Astronomers, peering into the deepest voids, use his work to decipher the faint, ancient whispers from galaxies millions of light years away. All of it, this intricate tapestry of existence, rests upon this singular, strange, yet utterly constant truth. Light possesses an ultimate velocity, and that velocity remains precisely the same for everyone, everywhere. So the next time a luminous sunbeam spills across your path, or a distant beacon flickers in the velvety dark, pause for a moment to truly marvel at what that light embodies. Not merely energy, not just warmth, but the exquisite, delicate geometry of space-time itself. A hushed pact penned in the very language of light. And no matter how swiftly you journey, no matter how far your quiet vessel drifts through the endless night, it will always greet you at the same serene passage, changing, unwavering, and eternally on time. We've journeyed through the essence of light itself, its fundamental nature, the ingenious ways its speed has been measured, and the profound reasons why the universe insists on bestowing upon it such a precise and immutable limit. But now, as your ship makes a subtle, almost imperceptible adjustment, perhaps a soft thrumming resonating through the hull, let's gently expand our view. Let's pull back the camera, so to speak, and truly observe the astonishing impact this cosmic speed limit has on reality itself. Because once you grasp that light simply cannot accelerate beyond its inherent pace, the implications, stretching across the entirety of existence, are unexpectedly vast and, in so many ways, profoundly beautiful. Let's begin with something utterly fundamental to how we comprehend the universe: time. Not the ticking of a kitchen clock, certainly, but the profound, flowing river that braids together events, memories, and the relentless march of causality. The speed of light imprints a magnificent structure upon time itself. It draws invisible, yet unbreakable, boundaries around what can possibly influence what. It whispers to the universe, you may only connect these disparate dots if there is ample time for light to traverse the space between them. This profound concept is what physicists affectionately term the light cone. No, it's not a delightful frozen dessert, nor is it a curious lampshade. Rather, it's an elegant, almost poetic, way of mapping out precisely which segments of space-time are intimately linked by cause and effect. Imagine, if you will, a fleeting mental projection on the ship's viewport. You're standing in a vast, empty field, and with a soft click, you ignite a tiny match. That incandescent spark immediately begins to radiate light outward in every conceivable direction. The furthest anything can be directly affected by that tiny flame, whether instantly or eventually, is unequivocally limited by how far that light can journey from that very moment onward. If someone were situated truly, impossibly far away, say, 100 light years distant, they wouldn't even perceive the match was lit until a full century had gracefully passed. Now, let's gently flip that perspective, shall we? Imagine yourself once again in that same boundless field, but this time, you are simply waiting for something to occur. The only events that could conceivably influence your present moment, right here, right now, are those whose light has had sufficient time to reach you. This is your past light cone, a luminous, invisible bubble encompassing everything that could have possibly contributed to your current existence, your very now. The light cone isn't merely a clever diagram. It represents the precise, unyielding border between what is possible and what remains, for now, impossible. If an event transpires beyond your light cone, it's not simply too far away in terms of distance. It is too far away in time. No signal, no resonant sound, no gentle whisper from that distant happening can yet reach you. It is, for all intents and purposes, as if it doesn't exist for you at all. Not until its ancient light finally arrives. This profound idea utterly reshapes our entire understanding of the universe. It means there's no such thing as instant communication across cosmic distances, no perfect, universal synchrony, no singular, omnipresent now that blankets all of existence. Instead, every moment is exquisitely local. Every now subtly differs, a unique temporal experience, depending on your precise location and velocity. And the steadfast speed of light serves as the ultimate rulebook, maintaining this grand, consistent order. Consider how this magnificent concept influences your gaze upon the night sky through the panoramic viewports. When you peer at those glittering stars, you aren't witnessing them as they are in this precise instant. No, you are seeing them exactly as they were, perhaps eons ago. The very light from our nearest stellar neighbor, Alpha Centauri, has been on its solitary journey for over 4 years to reach us. So, if something truly dramatic unfolded there just last week, we won't even begin to grasp it for several more years to come. And that's merely our immediate cosmic neighborhood. Gaze further out into the truly fathomless depths, and the effect becomes even more profoundly dramatic. The light from the majestic Andromeda galaxy has been traveling for over 2 million years to finally grace our eyes. You are witnessing it as it appeared when our early human ancestors were just beginning to whisper tales and forge their very first tools. Beyond that, you watch the ancient starlight spill across the view screen, a gentle, shimmering tapestry that feels so impossibly close, yet holds within it the whispers of ages long past. Each photon, a tireless traveler, began its journey billions of years ago, a silent testament from a time before our own sun had even ignited its fiery heart. The console lights around you cast a soft, rhythmic pulse, reflecting the cosmic dance outside, while the ship's gentle, almost imperceptible vibration hums a lullaby through the deck plating. Can you feel it? This deep, quiet sense of connection to something so profoundly old, yet utterly present. It's truly magnificent, isn't it? The way these light beams, moving at their own patient, unwavering pace, carry with them a chronological record of the cosmos. This inherent delay, this cosmic postal service, is precisely what transforms our telescopes into exquisite time machines. When we gaze into the deepest reaches of the void, you see, we're not merely observing distant space. We are peering directly into bygone epochs. It's the universe's elegant design, allowing us this extraordinary glimpse into its own sprawling history, all because light chooses a finite speed. A neat trick, wouldn't you say? And this speed limit isn't just a fascinating quirk. It's the very backbone of cosmic order, a silent safeguard preventing the universe from unraveling into a tangle of paradoxes. Imagine if signals could travel instantaneously, or worse, faster than light. Chaos would undoubtedly ensue. You might, perhaps, send a message to your past self, a whimsical warning like, "Don't, under any circumstances, try that suspicious-looking space burrito." But then, if you heeded your own advice, you'd never have needed to send the message in the first place. Why does the universe always do this to you? It's the kind of perplexing loop that truly tests the sanity of theoretical physicists, causing a gentle shift in your own perception of time. Thankfully, the speed of light acts as an unbreakable cosmic speed limit, ensuring that such baffling temporal loops remain firmly in the realm of science fiction. Consequences, blessedly, always follow their causes, and events unfold in a sensible, sequential manner. The past remains behind us, a fixed landscape, while the future patiently awaits ahead. This isn't just about the flow of time itself. It's the fundamental structure of time, woven into the very fabric of existence. The recycled air feels cool and clean against your skin as this grand cosmic rule settles gently in your mind. This profound principle even touches your terrestrial life. Consider the simple act of connecting with someone back on Earth. When you send a message or make a call, you might not consciously ponder the speed of light, but even across a planet as relatively small as ours, there's a whisper-thin delay. Your digital words, transformed into electromagnetic waves, bounce through satellites or race along fiber optics, moving at light speed. Yet, even at that astonishing velocity, a tiny, measurable moment passes, affirming that distance always requires time. Now, extend that thought to our distant robotic explorers. When Mission Control transmits instructions to a rover exploring the ruddy plains of Mars, that signal can take anywhere from 4 to a full 20 minutes to make the journey, depending on the planet's orbital dance. Imagine the patience required. If that plucky little rover were to, say, stub its robotic toe on a Martian rock, the engineers back home wouldn't even receive the telemetry for nearly half an hour. There's simply no real-time remote control out here. The speed of light dictates that these intrepid machines must be remarkably autonomous, making their own critical decisions, because, in the vastness, you're truly on your own. Even your favorite late-night documentary stream back home, every pixel and frame that unfurls across your screen honors this universal constraint. Each bit of information travels from distant servers across intricate networks of cables and switches, as pulses of light, all bound by the universe's built-in pace. It might initially sound like a limitation, a cosmic barrier, but truly, it's a profound kind of harmony. It's what gives our universe its predictable elegance, where every effect has a cause, where the past is immutably set and the future unfolds with purpose. This invisible rule lends structure to both space and time, transforming what could be an endless, featureless void into a magnificently ordered tapestry of interconnected events. It's perhaps a strange thought, isn't it, that the very fastest thing in the cosmos is also the very thing that gently slows down how quickly we can comprehend something has happened. Yet, it's precisely these tiny, inherent moments of waiting, this essential delay, that render the universe understandable. They grant us distance, offer perspective, a little room to think, and perhaps, just perhaps, a quiet space to rest. Let's imagine, just for a moment, that you're not the kind of person who readily accepts every no the universe throws your way. You've heard all about this cosmic speed limit, this fundamental traffic rule etched deep into the laws of physics. And naturally, your mind begins to wonder, what if we just ignore it? Could anything at all, ever actually move faster than light? It's a wonderfully tempting thought, isn't it? After all, humanity has a rather impressive track record of pushing boundaries. We've shattered the sound barrier, dispatched clever robots to Mars, and even built colossal machines capable of dissecting atoms. So, what exactly is preventing us from discovering some ingenious cosmic shortcut? Something that zips along faster than a dizzying 299,792,458 meters per second. The faint engine hum in the background assures you we're quite stable for now. Well, down in the labyrinthine basements of theoretical physics, there's a curious little whisper of an idea: tachyons. These entirely hypothetical particles were conjured up within certain equations, and they come with an utterly eyebrow-raising feature. They can only travel faster than light. In fact, they supposedly couldn't even slow down enough to reach light speed. That's their unique inverse limit. Sounds incredibly exciting, doesn't it? A particle that inherently disregards the cosmic speed limit, darting through the universe like a hyperactive squirrel on a triple espresso. There's just one rather significant problem, though. No one, anywhere, has ever actually found a tachyon. Not nestled in the data from a lab experiment, not lurking suspiciously in the vast silence of deep space, nor even hiding coyly in the margins of those very equations. They remain, for all intents and purposes, a delightful rumor in a cosmic small town, always mentioned, never quite seen. And even if these elusive particles, did exist, they'd likely unleash more havoc than they'd solve. If you could harness them to transmit information, you'd swiftly violate causality, meaning you could send a message right into your own past. And if you've ever seen a time travel movie, you know precisely how messy that can get. Grandparents vanish, timelines collapse, and everything just starts to unravel. So, most theoretical physicists politely agree. Tachyons are fascinating to ponder, but probably not quite real. They belong in the box marked interesting. But nope, the subtle movement of the ship reminds you that reality has its own rules. But what about other phenomena that seem to defy this cosmic speed limit? Let's turn our attention to quantum entanglement, arguably one of the spookiest, most perplexing phenomena in all of physics. Imagine two particles that become inextricably linked or entangled. The moment you measure a property of one, its twin, no matter how astronomically far away it might be, say, on the other side of a galaxy, seems to react and instantly correlate its own state. It feels like a cosmic cheat code, doesn't it? Surely, this instantaneous connection must be traveling faster than light. You might need a moment to just float here and ponder that. They arrive instantly, yet bring no messages, carry no secrets we can decode. It's quite peculiar, isn't it? You see, there's simply no way for us to influence what one of these particles decides to do when observed, which means it can't be used to convey anything useful. Imagine, if you will, two individuals separated by light years, each flipping an identical coin at precisely the same moment, and astonishingly, the results always match. Heads for heads, tails for tails, across the cosmic ocean. But here's the catch. Neither person can use this uncanny synchronization to simply say hello. A perplexing cosmic silence, wouldn't you agree? Even the brilliant mind of Einstein found this deeply unsettling, dubbing it spooky action at a distance. Yet, countless modern experiments have patiently, meticulously confirmed that this strange connection, this quantum entanglement, is very much real. However, it steadfastly refuses to bend the cosmic speed limit. No information travels faster than light. The universe, it turns out, is indeed a place of profound mysteries. A little spooky, as he put it, but ever so polite and respectful of its own fundamental rules. You can almost feel the gentle thrum of our ship's engines, a soft vibration through the deck plating, a quiet acknowledgement of these universal truths as we drift. Then there's another curious phenomenon, a whisper of glowing weirdness known as Cherenkov radiation. This ethereal blue luminescence appears when a charged particle glides through a medium like water, for instance at a pace exceeding the speed of light asterisk within that particular medium asterisk. Yes, you heard that correctly. Light, in its incredible journey, doesn't always race at its absolute maximum velocity. When it traverses materials such as glass, water, or even plastic, it slows down ever so slightly, gently nudged and delayed by interactions with the atoms it encounters. It's like a quiet sigh from the universe, allowing a tiny local exception. So, when a swift particle happens to outpace that asterisk-reduced asterisk local speed of light, it creates a kind of radiant shockwave, much like the sonic boom of an aircraft breaking the sound barrier. This is the very essence of that haunting, deep blue glow you might observe, emanating from nuclear reactors submerged in cooling pools. It's not that anything is truly shattering the ultimate universal speed limit. Rather, it's just briefly surpassing the asterisk local asterisk speed limit set within the material itself. Light in the vast emptiness of a vacuum still reigns supreme, untouched. No grand cosmic laws are broken here, merely bent with a quiet elegance in the quiet depths of a pool. A brief, beautiful anomaly, wouldn't you say? But what about truly pushing beyond, going that extra mile across the cosmos? Could we construct something akin to the fabled warp drives from those classic tales of science fiction? Could we, perhaps, bend the very fabric of space itself instead of merely journeying through it? In theory, the answer is a tantalizing maybe. One fascinating concept put forth in the 1990s by physicist Miguel Alcubierre suggested it might be possible to gently contract the space directly ahead of a spacecraft and simultaneously expand it behind. Our ship would then effectively surf this cosmic wave of warped spacetime. This clever maneuver would mean our vessel itself would technically never exceed the speed of light. Asterisk within asterisk, its local bubble of space, yet it would still arrive at its distant destination far sooner than a beam of light could on its own. It's an elegantly imaginative workaround, a cosmic shortcut, but like many grand ideas, it arrives with a few significant complications. First, it would demand a substance possessing negative energy density, a form of exotic matter for which we currently have no tangible evidence, nor any real understanding of how to conjure it into existence. The faint hum of our ship's life support system whispers around us, a constant reminder of tangible engineering. Second, even if such a remarkable feat of engineering were somehow achievable, the sheer energy requirements would be, well, monumental. We're talking energy on a planetary scale. Some calculations whimsically suggest you'd need the equivalent mass energy of Jupiter just to propel something as small as a grapefruit. So, for the moment, warp drives remain firmly nestled within the inviting realm of our collective imagination. They're splendid for fueling our stories, of course, but prove considerably trickier for practical engineering. And isn't that just like the universe, giving us such grand ideas only to keep them just out of reach? Then there are wormholes, those hypothetical tunnels through the intricate tapestry of space-time that could, in theory, connect to vastly distant points instantaneously. Think of them as cosmic shortcuts, or perhaps space-folding bridges, allowing us to traverse unimaginable distances in a single ethereal leap. Again, the profound mathematics of the universe gracefully permits their theoretical existence. But, yet again, the practical problems swiftly begin to stack up. Questions of stability, the inevitable need for that elusive, exotic matter, and the dizzying specter of time paradoxes. It's like trying to construct a robust suspension bridge using nothing but soap bubbles and unwavering hope. And even if you could somehow coax one into stable existence, it wouldn't truly be faster than light travel in the conventional sense. You'd merely be selecting an incredibly shorter path through the existing framework of spacetime. The light still wins the cosmic marathon, always moving at its inherent pace, but you've ingeniously discovered a convenient, almost magical, side street. Our ship glides through the inky blackness, the distant starlight reflecting in gentle shimmers across the main view screen, a silent witness to these theoretical wonders and their practical limitations. So, where does this fascinating journey leave us? Despite all these ingenious concepts and curious theoretical exceptions, nothing with actual mass or information has ever been observed traveling faster than light. Every time we believe we've uncovered a clever loophole, the universe, with an almost imperceptible shrug and a quiet, knowing smile, simply steps in and gently closes it, perhaps with a raised eyebrow and a chalkboard full of elegant equations. And perhaps, just perhaps, that isn't such a bad thing after all. You might need a moment to just float here, letting that sink in. The speed of light might initially feel like an irritating restriction, a locked door standing defiantly at the very edge of possibility, but in reality, it's far more profound. It's akin to a cosmic safety rail, elegantly preventing the entire universe from spiraling into paradox, utter chaos, and frankly, utterly bewildering spaghetti timelines. It grants us structure, provides a fundamental order, and imbues us with a serene sense of cosmic peace, knowing that no matter how strange or wondrous things become, there are still inviolable boundaries that even the universe itself respects. The subtle movement of our ship, a gentle sway, echoes this inherent order. So, if you ever find yourself gazing out into the boundless expanse, perhaps wishing you could instantly beam across the stars, or send a message to your past self about tomorrow's weather, take profound comfort in this quiet truth. Light itself, swift, silent, and wonderfully steady, is already moving as fast as anything possibly can. It is, and always has been, leading the way. And perhaps, just perhaps, that is more than enough. By now, you might be sensing a deeper pattern emerging from our discussions. The speed of light isn't merely some arbitrary numerical value. No, it's a profound cosmic foundation stone, meticulously woven into the very fabric, the intrinsic architecture of the universe itself. But what if it's whispering something even deeper to us, something more profound than we currently realize? What if that mysterious, almost poetic number, 299,792,458 meters per second, isn't just a simple limit on velocity, but rather a crucial key to unlocking our understanding of space, time, and indeed, reality itself? Let's take a relaxed stroll into one of the more philosophical corners of physics. Don't worry, we're keeping it cozy. You can absolutely keep your slippers on. One of the most intriguing concepts in modern physics posits that the speed of light isn't solely the brisk pace of a photon, but instead a fundamental conversion factor, a seamless bridge between the dimensions of space and time. That iconic number, which we'll simply call c for convenience, is what permits us to fluidly translate distance into time and then back again. It acts like the universe's built-in universal translator, allowing these two seemingly distinct concepts to speak to each other. You've likely encountered its silent presence in Einstein's most celebrated equation, E equals mc squared. Here, the speed of light appears as a powerful link, an energetic bridge connecting mass and energy. It precisely informs us just how much astonishing energy is intrinsically locked away within a given amount of mass. But C also makes its recurring appearance throughout the theories of relativity in the elegant equations that describe time dilation, the subtle phenomenon of length contraction, and the intricate curvature of space-time itself. The fact that it consistently emerges, woven into the very mathematical descriptions of our reality, is certainly no mere coincidence. It's a profound hint that c is far more than just a speed. It's a kind of universal glue. The recycled air, cool and clean on your skin, whispers of these connections. Let's gently explore that idea with a simple, calming thought experiment, shall we? Imagine, for a moment, that the universe around us is like a magnificent, intricately woven fabric, composed of both space and time, not as two distinct, separate threads, but as one singular, unified material, space-time. This concept, while perhaps sounding like a fantastical science fiction buzzword, is remarkably real and profoundly fundamental to our understanding. In Einstein's groundbreaking theory, space and time are not merely independent dimensions. They are deeply intertwined, inseparable. They behave, ... Drifting gently, you feel the subtle tremor of the ship, a soft vibration humming through the hull that reminds you of its incredible journey. You're not just moving through the vastness of space, are you? No, you're also gracefully navigating the currents of time itself. It's a beautiful dance, really. When our little vessel picks up speed, time, from our perspective, begins a gentle deceleration, a quiet slowing down. And when some colossal star or distant galaxy pulls with its immense gravity, it doesn't just tug at space, it delicately bends time around it too, like a ripple in a cosmic pond. But there, right at the heart of it all, is the luminous whisper of the speed of light, that magnificent, constant c. Think of it as the universe's own perfect conversion rate, an elegant exchange desk where meters and seconds are not just traded, but inherently intertwined. This is why we speak of light years, not as a measure of how long something takes, but how far light travels in that span. Isn't that just like space, to weave them so tightly? This cosmic constant, this steady pulse, acts like the invisible stitching that holds the entire quilt of reality together, doesn't it? There's a profound calmness in knowing that, an inherent consistency built into the very fabric of everything. No matter how far we drift, no matter how quickly we glide through the quiet dark, C remains precisely the same. It's the universe's unwavering heartbeat, ensuring that the grand equations of physics behave themselves, keeping cause always gracefully ahead of effect, even at the dizzying edges of black holes or within the fiery hearts of distant galaxies. In fact, many brilliant minds don't even treat c merely as a speed anymore. In their more elegant equations, they simply set its value to 1. Not out of laziness, of course, but because it brings a sublime simplification, allowing space and time to be treated as perfect equals, perhaps a little elegant tidying up for the cosmos, wouldn't you say? And this leads us to an even more curious, almost dreamlike thought. Maybe the universe isn't just designed for light to move within it, but rather the universe itself is fundamentally built around the speed of light. Imagine, for a moment, being a tiny photon, one of those luminous little travelers, from its own perspective. The very instant it's born, and the very moment it's absorbed into something a distant eye, a far-off sensor, happens simultaneously. There is no ticking clock within a beam of light. Time, from that photon's point of view, simply doesn't pass at all. No ticking clock in there. Imagine that. It's a truly wild idea, isn't it? But it's softly, steadily backed by the whispers of relativity. The faster you journey, the slower your personal clock begins to tick, until, for something moving at light speed, the ticking simply ... stops. It exists only in its exquisite motion, a pure act of perpetual being. This brings us back to that poetic truth, doesn't it? Light isn't merely a passenger traveling through the universe. It actively defines the very structure of the universe as it goes. The speed of light isn't a choice light makes. It's something the universe quietly, firmly insists upon. We've even reshaped our most fundamental units of measurement around this celestial speed. Since the year 1983, our familiar meter, that everyday measure of distance, has been precisely defined by how far light gracefully travels in just one incredibly tiny fraction of a second, specifically 1/299,792,458th of a second. That's not just poetic, that's profoundly precise, a cosmic blueprint. We've made the speed of light the ultimate rulers are measured, our universal yardstick for both the vastness of space and the flow of time. Nothing to worry about though, just the universe showing off its beautiful precision. And perhaps that's the most grounding, most comforting part of all this. In a universe that can often feel so incredibly vast and utterly strange, filled with the mysteries of dark matter and the fleeting uncertainties of quantum mechanics, there is this one beautifully fixed point. The speed of light is a constant you can build your world around, because, quite literally, we do. So, the next time you gaze at a gentle flicker from a candle, or watch the soft, ancient starlight filtering through the viewport of our ship, know this: you're witnessing so much more than mere brightness. You're observing a profound cosmic law in quiet, elegant action. It's a subtle message from the very geometry of space-time itself, a tranquil reminder that while the universe may be immense and mysterious, it is also quietly, exquisitely consistent. Light doesn't just illuminate our world, it sets the fundamental rhythm of the entire cosmos. Isn't that just the most beautiful secret the cosmos keeps? By now, you've hopefully seen how the speed of light isn't just some dusty footnote in physics textbooks, is it? It's the very pulse of the cosmos, the silent stitch in the fabric of space and time, the steady metronome that keeps all of reality in its perfect, flowing rhythm. But here's something that might genuinely surprise you. Even here, in the quiet expanse, the speed of light isn't just out there, floating between galaxies or bouncing off distant stars. Oh no, it's intimately woven into your everyday life, too. That's right. Even if you've never piloted a starship or built a particle accelerator in your backyard, though if you have, hats off to you, you're still living in a world shaped, defined, and subtly orchestrated by this very same speed of light. Let's think about something familiar, shall we? Your phone. Yes, that humble device you're probably holding or listening on right now. Every time you tap its screen, stream a video, or send a sleepy emoji to a friend, you're harnessing the silent, incredible power of light. Nothing to worry about though. Your cat videos are safe at nearly light speed. Specifically, you're engaging with light as it travels through slender, almost invisible fiber optic cables. These delicate strands of glass or plastic are truly the nervous system of the internet, aren't they? They stretch in incredible networks beneath our vast oceans and across entire continents, forming a global web that carries information at nearly the astonishing speed of light itself. When you load a web page, you're not just waiting for a distant server to ponder your request. No, you're waiting for countless tiny pulses of light, those flashes representing the ones and zeros of data, to make their lightning-fast journey through these intricate cables, bounce through countless routers, and finally arrive at your screen. And while light does travel a touch slower in fiber than in the pristine vacuum of space, roughly 2/3 as fast, it's still astonishingly quick. We're talking about hundreds of thousands of kilometers per second. That's how your favorite cat videos, vital weather updates, and soothing bedtime playlists arrive with barely a whisper of a pause. These fiber optic cables aren't just moving, helping us navigate through the cosmic expanse. You might find it quite remarkable, truly, how something so foundational as the very speed of light underpins technologies we use every single day, right there on your homeworld. Take the Global Positioning System, or GPS, for instance. As you gaze out your viewport at the gentle curve of Earth below, perhaps a faint engine hum vibrating softly through the deck beneath you, imagine those tiny signals zipping when your device back home wants to guide you to that delightful little bakery for a fresh pastry. It's quietly reaching out to at least 4 satellites, invisible to the naked eye, but constantly whizzing in orbit. Each one broadcasts a precise timestamp, accurate down to a nanosecond, and your little receiver then compares those arrival times to pinpoint your exact spot. It's almost like asking a few friends how far they are from you, and then, quite cleverly, drawing circles to find yourself precisely in the middle. Simple, right? But here's where the universe gets a little playful, even with something as straightforward as finding a street. For that GPS to work with such astonishing accuracy, we must account for those 2 captivating theories we've been exploring: special and general relativity. Those satellites, you see, are moving incredibly fast relative to the Earth's surface, and because of that velocity, their onboard clocks actually tick just a fraction slower, a subtle nod to special relativity. Yet, at the very same time, they're much higher up, further from Earth's gravitational embrace, which causes their clocks to tick a little faster due to general relativity. It's a cosmic dance, a delicate balancing act. Without meticulously correcting for both these effects, your GPS would drift by several kilometers every single day. Can you imagine the frustration of missing your bakery by miles? Thankfully, Einstein's brilliant insights, alongside light's unwavering constancy, ensure you always find that craving satisfying croissant. Nothing to worry about, probably. Now, let's bring our focus in, away from the distant glow of Earth, perhaps to the very light reflecting off the smooth console in front of you, or even closer to your own eyes. Your entire perception of the world around you, your very vision, is intricately built upon the graceful ballet of light. When you look at the stars, or the quiet interior of this ship, What you're truly witnessing are countless tiny packets of energy, photons, bouncing off surfaces and gently entering your eyes. These minuscule travelers then journey through the cornea and lens, expertly focused onto your retina, where they trigger a cascade of chemical wonders within specialized cells. Your magnificent brain then takes those whispers of electrical signals and, like a master artist, reconstructs them into the vivid, colorful tapestry of a distant galaxy, a breathtaking sunset, or even that rather judgmental houseplant you once had back home. Isn't that just like space, making something so complex seem effortless? All of this exquisite sensory experience hinges on how swiftly light traverses its path, how it artfully bends when encountering different materials, and its delicate interaction with the atoms nestled within your retina. Even the astonishing fact that you perceive depth and the fluid flow of motion relies on the minute, almost imperceptible delay as light reaches each eye, allowing your brain to subtly compare the two inputs. And speaking of light's elegant bending, let's consider something called refraction, that charming phenomenon where light slows down and changes its course ever so slightly when it transitions into a different medium. It's the reason a humble straw appears to snap and jut at an odd angle in a glass of water, or why you see those mesmerizing shimmers on a blistering hot road in a desert landscape. This same principle is the quiet genius behind your eyeglasses, the powerful magnification of microscopes, the distant gaze of telescopes that pierce the cosmic veil, and the intricate lenses in your cameras. Every time you frame a memory with a photograph or settle down with a good book, aided by corrective lenses, you're effortlessly benefiting from our profound understanding of light's journey. Even the humble microwave oven, gently humming with its promise of reheated delights, owes its entire existence to electromagnetic waves. Microwaves, you see, are simply a lower frequency cousin to the visible light that illuminates our journey. They gently bounce around within the oven's chamber, causing the water molecules in your food to subtly jiggle and warm. Without this vast electromagnetic spectrum and our deep appreciation for light's properties, reheating those leftovers after a long spaceflight would undoubtedly be a far messier and, frankly, less cozy affair. Why does the universe always do this to you, making everything so interconnected? Let's take a leisurely drift now, a cozy step into the bustling realm of telecommunications, that favorite radio station from your home planet, whispering familiar tunes across the airwaves. That's just light, too, in a different guise. Radio waves are simply another part of this magnificent electromagnetic spectrum, possessing longer wavelengths than the light your eyes can perceive, yet still traveling at that same unwavering speed through the vacuum of space. They allow your ground car to belt out music as you cruise along, or perhaps transmit a distant signal to our own comms array. Television broadcasts, the invisible web of Wi-Fi signals connecting your devices. Even the subtle handshakes of Bluetooth, all of these are forms of electromagnetic radiation, quietly zipping through the void, guided by the very same immutable rules that govern the ancient starlight outside our hull and the precise beams of a laser. You might need a moment to just float here, suspended in the gentle shift of artificial gravity, and simply absorb that thought. And our journey continues, now wandering for a moment into the intricate world of medicine. Those rather ethereal, almost ghostly images of your bones, the X-rays you might have seen, are actually very high-frequency electromagnetic waves. They possess the remarkable ability to pass right through softer tissues, like muscle and skin, but are then absorbed by denser materials, such as your bones. This precise contrast is what creates those curiously skeletal snapshots. Even MRI machines, while not directly employing visible light, still harness powerful electromagnetic fields to construct incredibly detailed, almost three-dimensional images of the deepest interiors of your body. It's truly amazing, isn't it? In essence, light, or its vast, extended family of electromagnetic waves, is the quiet, tireless worker behind the scenes, weaving its magic into nearly every facet of our modern existence. It's how we truly see the world, how we communicate across vast distances, how we navigate our ships through the stars and our cars on busy streets, how we cook our meals, stream our entertainment, scan our bodies for health, and yes, how we even study the stars themselves. And speaking of those glittering celestial bodies, remember that every single piece of knowledge we possess about the universe beyond our own solar system has been lovingly delivered to us by light. Telescopes, like the iconic Hubble Space Telescope, patiently capture the most faint, ancient photons that have journeyed for literally billions of years across the profound vacuum of space. These venerable beams carry encoded stories, whispered across the cosmic canvas, tales of distant galaxies, swirling nebulae, enigmatic black holes, and even the very early moments of the cosmos's birth. We meticulously decipher these epic narratives by carefully analyzing the light's color, its intensity, and its unique spectrum. A minuscule shift in wavelength, known as a redshift, can reveal how rapidly a galaxy is gracefully receding from us. A barely perceptible dip in a distant star's brightness might gently hint at a planet discreetly passing in front of it. And a strange, uniform glow, observed throughout the background of space, could just be an ancient, echoing whisper from the very Big Bang itself, a cosmic sigh heard across unimaginable eons, and the most beautiful part of this grand celestial tapestry. It all functions perfectly because light adheres to the same steadfast rules everywhere, always. Whether it's a photon playfully bouncing off your coffee mug right here on the ship, or a ray of starlight that began its journey from a galaxy 13 billion years ago, it travels with the same unwavering, rock-solid speed. So, the next time you casually open an app on your device, or simply glance up at the moon hanging in the dark canvas of space, take just a quiet moment to truly marvel at the profound wonder unfolding. It's the quiet, graceful dance of countless photons, the unseen ballet of electromagnetic fields, and the unshakable certainty of universal constants. It's the steady, tireless motion of light racing around, through, and within your world, all at that one astounding speed. 299,792,458 meters per second. Light isn't merely a magnificent cosmic phenomenon, it is quietly nestled in your pocket, warmly illuminating your home, and intricately woven into your very eyes. It is the silent, efficient engine of the everyday. Take a moment, if you will, to simply envision a single beam of light drifting, utterly alone, through the vast, profound emptiness of space. No planets to pull at it, no stars to guide it, no gravity to hinder its path. Just one solitary photon, gliding effortlessly through the vacuum, neither quickening nor slowing its pace. It possesses no mass, knows no rest, and needs no fuel. It simply exists in motion, forever moving at the only speed it knows, 299,792,458 meters per second. That image, simple and serene, is more than just a scientific concept. It is a profound meditation on pure, unburdened existence, a journey without end. Here, floating gently with the subtle thrum of the ship beneath us, the distant console lights casting a soft blue-green glow across the panel, you might feel a profound sense of peace. That quiet hum you hear, a blend of life support and faint engine vibrations, creates a perfect backdrop for a thought, a truly cosmic musing. You see, this journey isn't just about us moving through the void. It's about understanding the very essence of what allows us to see the void at all: light. This humble, tireless traveler is not merely traversing distances, it's weaving the great tapestry of the cosmos, a delicate yet powerful dance of information, energy, and time that underpins everything we comprehend. It's the universe's own silent symphony, playing out across billions of years. Imagine, if you will, the oldest whisper in the universe, the cosmic microwave background. This isn't some abstract concept, but the actual, primordial glow from the dawn of time itself. It's been on an uninterrupted journey for almost 14 billion years, a faint, uniform warmth that bathes every corner of existence. It's not the sharp brilliance of a supernova or the soft luminescence of a nebula. Oh no, this is the cooled-down memory of when the universe, roughly 380,000 years after its fiery birth, finally cleared its throat. Before that moment, the cosmos was a dense, impenetrable haze, too hot and chaotic for light to travel freely. Just a soupy fog, really. But then, as temperatures gently eased and neutral hydrogen atoms formed, the universe became transparent, and suddenly, light was free. It burst forth in every direction, an ancient ocean of radiation, now stretched thin by the ongoing expansion of space, reaching us as gentle, microwave whispers. Think of it, when our instruments on Earth, or even here on the ship, detect the CMB, we are quite literally catching photons that have been traveling since the very first moments of clarity. These tireless particles, never truly resting, have crossed untold billions of parsecs just to land softly in a sensor, carrying a message. Here's what it was like back then. Isn't that just like space? A profound act of cosmic archaeology. Yet this story of light is far from over. Doesn't merely recount our distant origins. It actively binds the present, influencing everything you're experiencing in this very moment. From the majestic gleam of stars painting the viewport to the intricate dance of atoms within our hull, light is the quiet, ubiquitous participant in every process. Take photosynthesis, for instance, the fundamental engine of almost all life on that distant blue planet we sometimes call home. It all begins with a single photon, a tiny packet of light from the sun striking a leaf. This gentle impact excites electrons within chlorophyll molecules, initiating a beautiful chain of reactions that carefully stores energy in chemical bonds. Plants then use this stored energy to grow, reaching for the very light that sustains them. Animals graze on the plants, or on other animals that did the grazing, and so the vibrant, intricate chain of life continues, unbroken. Without light, no photosynthesis. Without photosynthesis, no plants. And without plants, well, let's just say your dinner menu would be considerably less inspiring, wouldn't it? In a very real sense, every meal you've ever enjoyed began its journey with a photon, a tiny messenger of energy from our distant sun. Nothing to worry about, probably. And it's not just the green things on planets that cleverly interact with light. Our own bodies are exquisitely tuned to capture and respond to its subtle cues. Your internal clock, your circadian rhythm, is deeply, intrinsically influenced by the light around you. As the ship's simulated daylight gently shifts, perhaps mirroring the subtle changes outside, if we were closer to a star, your body receives these signals. A burst of morning light, whether real or artificial, tells your brain to slow its melatonin production, that lovely hormone that invites you to drift off as the simulated dusk descends, allowing for rest in the ship's quiet chambers. Fading light encourages melatonin to rise again, gently guiding you toward a peaceful slumber. Even now, as you listen, your very being is tracking these luminous shifts, adjusting its rhythms, settling into the world's quiet, ambient flow. But perhaps the most truly profound magic of light is its capacity to connect. It's not just a bridge between your eyes and a distant nebula, or between a star and a telescope. It links moments in time, experiences, to understanding. It is the fundamental conduit for information across the universe. Every time you glance across the quiet console or gaze through the viewport into the endless velvet black, you are receiving messages, waves of energy shaped by the vastness of space and translated by your own remarkable mind. Light is, in essence, the very language of the cosmos. And like any rich language, it boasts countless dialects, a spectrum of wavelengths, each telling a different story, a different truth. Some of these dialects whisper tales of the chemical makeup of galaxies so far away they are almost dreams. Others, with a sharp, urgent tone, warn us of gamma-ray bursts, the most energetic explosions in existence, a fleeting cosmic scream. Some carry the soft, warming embrace of infrared radiation from a newly forming star, swaddled in its dusty nursery. Still others paint ephemeral rainbows across a stray oil slick on an alien sea, or within the delicate film of a soap bubble, revealing the hidden geometry of interference and refraction. This incredible diversity is precisely what makes light such an extraordinary messenger. It doesn't just show us what is there, it meticulously reveals how everything works. Think of a simple prism, splitting a beam of pure white light into a breathtaking symphony of colors, each frequency a note in the universe's grand composition. Or the light arriving from a supernova, carrying the unmistakable fingerprints of heavy elements forged in the unimaginably violent furnace of a dying star flung across the cosmos. And the most remarkable part, we, in our curious human way, have learned to listen better, to read these cosmic messages with increasing clarity. With our radio telescopes, we can perceive the subtle whispers of vast, cold hydrogen clouds patiently waiting for stellar birth. Our X-ray telescopes let us peer through the veil, seeing the very skeletons of galaxy clusters glowing with superheated gas. Infrared instruments allow us to pierce through obscuring cosmic dust, granting us a privileged view of stars being born. We've even developed detectors for gravitational waves, attuned not to light, but to the very ripples in space-time itself. Another cosmic messenger, complementing the ancient tales photons have always told. All of this, as we drift silently through the void, paints a picture of a universe that is anything but a cold, silent expanse. Instead, it's a vibrant, living entity, overflowing with signals, rich with stories, and utterly saturated with light. It's a gentle reminder that we are not separate observers, merely watching from afar. No, you are bathed in it, shaped by it, an intrinsic part of it all. The very atoms that form your being, the carbon in your cells, the calcium in your bones, the iron coursing through your blood, were forged in the fiery hearts of stars that blazed billions of years ago. The light from those ancient suns journeyed across interstellar space, touching gas clouds, seeding new solar systems, carrying the very raw material of existence. That same relentless process created you. You are, quite literally, made of star stuff, carried here by light.